Hello and good morning, good night, or good evening, everyone, depending on wherever you are in the world. And welcome to this practical session from MRI Together. In this ending part of the MRI Together, we have practicals, which are basically, as the name suggests, they're practical sessions. So you're going to learn how to implement the stuff that we have heard about during the MR together in practice. And these sessions are a bit longer than the previous ones. Each talk is 1 hour instead of 20 minutes. And we hope you enjoyed. The first speaker is Sebastian, who's going to present an interesting topic and an interesting problem that all of us have. But yesterday it worked on my machine. So the floor is yours.
And here we already have the first problem that worked on my machine yesterday. You have to stop sharing so I can share, please.
Oh, okay.
I'm sorry, that might have been my fault.
Yeah. You have to move me, I think.
Okay.
Right. Okay, so I hope this works now and we can see everything. So yeah, yesterday it worked on my machine. That's my topic for today. And we will discuss some common problems in projects you might have encountered in the past or you might encounter in the future. One of the biggest problems is versioning. I think you all have seen these like, oh, this is my final draft, or this is my final draft, and these kinds of files. You might have some surprising delivery dates, like, oh, we have to deliver something tomorrow, or your software might break because your dependencies change. There is one important solution to that, and that's plan ahead. Use some version control, use continuous integration or delivery, and, for example, use containerization to keep your dependencies in check. So if you have ever found yourself in one of these situations, like what I just said before, you have paper draft, final 2, final 3, there is some work in progress text files or a submitted paper, or you have some version issues with syntax errors because you're using a different Python version than your colleague was using before, or you have to deliver something tomorrow but nothing's working yet, then this talk is for you. My name is Sebastian Höffner. I am a DevOps engineer at Fraunhofer Mewis, and I have been in these situations in the past, and I will guide you through some solutions and argue that these solutions are not only important in software engineering, but they are also very important in science. You already saw that I applied it to a paper draft here, and that's one of the things where I use all these solutions for whenever I do it. I will also happily answer any questions should they come up, although I'm not sure if I can see the chat because of the screen sharing things here. So maybe Mo has to jump in then. All right. So the origins of the paper draft, final, copy 2, 3, text file, whatever madness. Very often this is just because we add these final suffixes ourselves. Sometimes you get those copy 2, for example, because you're making a copy of a file just to be sure that you keep this version. Maybe this sentence is nice, or maybe my algorithm here worked pretty good and I don't want to screw up, something like that. And sometimes tools simply add some prefixes or suffixes. So for example, if you ever used Dropbox to work together with your colleagues, and some of you were editing the same file, Dropbox will happily create a copy of the file to simply avoid certain conflicts. Because if I change something in my Word document and you change something in yours, then we might have a conflict and we can't resolve that. What's the reasons to do so? So one of the biggest reasons is backupping your work. So it's not really a backup in case your hard drive fails or something like that, but it's more like a form of versioning. So you would say, oh, this is now my final version. I want to submit this and I want to always be able to find it again. Or this is the camera ready version for my paper. Or this is, I don't know what kind of version 1.0 of my awesome script here. Another reason is sharing and reviewing. So if you, for example, send your paper to your colleagues, then you want to know which version of your paper they reviewed. You might have done some changes in the meantime and all these kinds of different things. So you might want to be able to go back to whatever version they reviewed so that you can incorporate all their comments. But also, as I already told you, sometimes we just want to collaborate. So we jump into Dropbox or Overleaf or whatever, write something, and eventually we end up with multiple files. And one reason why we do that as well is our tools sometimes just don't support proper versioning. If you try to use Microsoft Word and try to, I don't know, like create a final version or a camera ready version or whatever, it's very difficult to actually get it to do that and to be able to roll back to whatever kind of version you want to have. So there are many different reasons why we end up with a folder full of these files, which essentially all contain the same things, but at different points in time. But that causes some problems. So if you, for example, want to compile this paper now, you don't know which file you have to compile. You might even have files where you like include some other files and now their names changed. So everything is very difficult, becomes very brittle, and there will always be a more final version. So you might change because there is a typo somewhere and then already, oh, now I have a final version. So files can get out of sync, everything can break, and it's really difficult to keep track of all the changes. Additionally, which is usually not the problem with small text files, storage requirements can grow a lot. If you have text files and you, for example, a PowerPoint presentation can have multiple megabytes, and then if you have a copy and a copy and a copy and a copy of that, it will simply grow. So what's the solution to that? The simplest solution today is to use a version control system or version control software. And the biggest on the market right now is Git. Git is a tool which allows you to store files and the changes you make to the files on your computer, on your colleagues' PCs, on some server you have in your company or in the cloud or wherever. It allows you to sync all those changes. So whenever you have made a change, you can just publish it and everybody else can get the changes as well. It will even help you to fix conflicts. So if you have changed your abstract and your colleague also changed your abstract, then it will tell you, oh, you both changed your abstract. Here is a conflict and I don't know what to do. Can you help me fix it? So it allows you to sync up, to work together without all the hassle of creating different files. It also enables experimentation. So it allows you to try something out on a so-called branch, and then you can essentially try it. And if you like it, you can incorporate your changes. And if you don't like them, you can just throw them away. So there's many different use cases for using this kind of system to get actually work synced up, get it together, and work together. You can also compare versions. That's very important because if you work together on your abstract, then you will have different versions of the abstract and you have to know, oh, what changed in which version and how does it look on my current, let's say, main version. It allows you to create tags, or let's call them bookmarks for this case, of your version. So you could simply say, okay, this version is now the one I gave my colleague to review. This is the one I submitted as the camera ready or for the reviewers or something like that. So you can always keep track of all the different versions, and you can give them some semantic bookmarks so that you always know, oh, I want to go back to the version I gave to Mo, and I want to be able to actually see what he has to comment on that. And one of the biggest advantages of Git, which I would say is one of the reasons it works so well compared to many other distributed version control systems, and there are tons of them, is that it's integrated into many tools. So chances are that if you use some kind of IDE, so integrated development environment, that it already has some sort of Git support. So it can already use Git under the hood to tell you what your changes are right now, how you can sync up, and so on and so forth. And we will see that in a second. So you can ignore the text on the left. It's more for reference when you check the slides later, but important is now the things on the right. This is roughly how Git works. So you have a working tree. That's your directory on your computer with all the files in there. And whenever you do a change, you can add a change to the so-called staging area. The staging area is just a collection of changes. You can always inspect them, see, oh, okay, I like this change, let's keep it there. This change is not so nice, so you can reset it and basically just work on it a little bit more. And once you are happy with the changes in your staging area, you can commit to those changes. And that's exactly what Git says about that. It says, commit to this set of changes. Then you add some metadata there. You say, oh, now this is written by me. This is written today. And it does something. For example, you can add some notes there. There's always a so-called commit message, which, for example, would say, I changed the abstract. And if you commit to a set of changes, then Git will basically make that an atomic set of changes called a commit. And you can publish this. So you can essentially tell your colleagues, hey, I did this set of changes, check it out. So you push it to some remote host, usually a server somewhere set up, but Git is very flexible, so you can get very wild where you push things. But in general, we have something like GitLab or GitHub, where we push our changes to a so-called remote repository. And then our colleagues can do what we would do when they would push changes. They can do the opposite and pull our changes into their local working tree. So this is essentially the whole workflow, and there are only two places where you can get into trouble, and that is when you push or when you pull. Because if you push, there might be changes on the host already which are conflicting with yours. And when you pull, you might have changes which are conflicting with the ones on the remote host. So you sometimes have to do a so-called merge. Merging is a very important concept. In Git, we always say we have different branches. So for example, you might have a branch on this remote server and a branch on your server. Even your working directory is kind of like a branch. And sometimes we have to merge those branches together. This would roughly look like this. You do a set of changes, that's a commit here. Then you might do another set of changes, that's another commit. And then you can create a branch. You can say, okay, I want to work on the abstract now. And I don't really care what the other people do to the rest of the paper. They might change the conclusion, they can change the methods part, or maybe they add some references here or there, fix a typo. That would still end up on the main branch where we have all these different changes. Now, as soon as we are done with our abstract working, we can simply merge this abstract changes back into the main branch. And Git will figure out, oh, these changes, they go here, and those changes you made there, they go there, and everything is fine. Sometimes it happens that it will find, oh, someone else was also changing something at the abstract, then it will tell you, oh, there is a conflict here, we have to solve that. But in general, it works really well, especially if you keep all these branches small. So only work on the abstract, don't work on anything else in that case, or only work on the references section or whatever. So a branch is really just an abstract concept for a simple or a single line of development. And it's comparable to simply copying your files somewhere, making some changes in those files, and then copying the difference back. But it's a little bit nicer to do that with Git. So let's take a short look at how this works. This is already, again, just a cheat sheet for me so that I know what I want to do now. And we will simply jump right into action. Whoop, no. It doesn't show the right window here. All right. Is it? Yeah, okay. So let's create a project. So I already went to our GitLab here. It's one thing we have there. We can create a project. And this project contains one file. It's a README markdown. It has all these introductory texts and tells you how to work with it. And we can check this out. So if we check this out, we need our password here. Then we have a new directory. It's the MRI Together demo. And in this directory, we have a README file. Now, what we want to do is we want to eventually change this README file. And to see how we are doing, we can first check the Git status. And it will tell us, yeah, you are on the branch main. So similar to what you have seen in the branching image just a few slides ago. And it tells us that our branch is up to date with origin main. That's the name of the branch which is on our remote directory, so the branch on GitLab. It also says that it has nothing to commit and that our working tree is clean. That means we haven't created any changes yet, which we would publish to our colleagues. And it says that we don't have any changes which we should consider for committing. So let's quickly jump into this README file. We can add some text here. So MRI together is great. And we love to write markdown files. Okay. So now we changed our README file. And if we check our status again, we will see, okay, we are on the branch main. Our branch is up to date, but we have some changes which we haven't staged yet for committing. So what we have to do is, if you consider the slides before, we have to put these changes into our staging area. We can do that by simply saying git add the README markdown, and then we can see, okay, now it is a change to be committed because it is in our staging area. And it also tells us this is modified, and if you commit now, this will be a change that you commit. We can also check the diff of that file, so we can check, okay, what diff is there? And it tells us, yeah, you created or you added these lines. If we would have deleted lines, it would be red and with a minus here, but there are lots of ways to do that. Okay. So let's say this is fine. So we commit to some changes. We say we add text to the README. And now it tells us, okay, you created a new version, ADE2D1B. That's just a hash which contains all this information. And the Git status will now tell us, okay, your branch is ahead of the origin main branch, so of the remote branch, by 1 commit, because we created a commit which is not yet published. And we can publish this commit, but before we do that, we can simply look what we did. And we can see here in the log, okay, this is our commit. It's authored by me. It's authored today, like at 7:20. That's our local time here, so very early. And this is what it says. So it adds some text to the README. Okay, so let's publish. Okay, yeah, we will have maintenance work today, so you can ignore this remote stuff here. But once we published things, we can now refresh the website and we can see our changes here. And that's exactly what everybody else would do now. They could now do a git pull and they would receive all our new changes. Now the cool thing is we can also go to previous commits. So we just added this commit here. And if we go to our history, we can also say, oh, let's get back to the version before. So we just can go there. And as you can see in this version, the text we just added is not there yet because that was the initial version. So we can in a very simple manner, just go through all our history and figure out what was where. Okay, that's enough for the start of Git. And I think you got the basic idea why this is better than having final behind our README files or camera ready or whatever, because now we have the same file whenever we want to have it, and we always know what changed, when did it change, and why did it change. Okay. So are our problems solved? No, only the first one, the final versioning problem. We haven't tackled yet the versions for our dependencies, nor the deliveries tomorrow. And I will start with the last one here. So how can we deliver anytime? The big problem is always there is a deadline some point and we always start late. So we always start like, oh, tomorrow there's a big delivery. We have to ship our files for the journal in a zip file. They need all our plots. They need all our images and the text files and the PDF and I don't know. You might have project partners who want to have your software packages. You might have a website which always needs to be up and running and needs the newest versions. All these things should be tested and they should work. And they should work tomorrow. No, actually now. Maybe even yesterday. So we all need to ship. And the best solution to that is to always use continuous integration and, if possible and required, continuous delivery. So what is that? So imagine you use a simple solution. You will always have this developer, let's call her Jane, and she builds everything every day. So she always goes there, compiles your code, creates a PDF, uploads it to some server, so you can always get the PDF or the latest package version or something. But imagine you were Jane. That would be a lot of unnecessary pressure on you, right? Because now you are in charge of always creating the latest release. What if your notebook breaks? What if you need a different toolchain because you're also working on a different project? So, for example, one project might have to be compiled with compiler version 9 and the other one with compiler version 11. What if you are on sick leave or on vacation? Or in the worst case, you get hit by a bus today? Then your team will be very sad that they only relied on you. And it's just not feasible to keep doing that. So instead, you should use a continuous integration approach and automate everything. So when Jane was writing all her scripts to actually compile things and so on and so forth, she took it a step further and just put all these build scripts she did into a build pipeline, which a server can happily run whenever you publish any changes. So for example, when we just submitted the README file, we could have, I don't know, rendered it to a PDF file or something like that. And that could have worked on the server. So you should always let a build pipeline, which is what we call this, take care of all these changes. This also helps you that you don't forget anything. So you don't forget to, for example, run your linter or type checking if you're using Python development. Or you will never forget to run your unit tests, which you hopefully write, and we will learn more about tests later today. And you can, of course, also run it for many different system configurations. So for example, let's say you support Python 3.5, 3.6, and 3.7. You can simply run your tests for all these versions, which is very difficult to do when you're only on your local computer. So let's see how this works in practice. So I created another project, the MRI Together CI demo. And there is a pipeline here. It's not so sophisticated as the one we just saw there. It has 3 different jobs. So it tests my code for Python 3.5, Python 3.6, and Python 3.7. And as you can see, everything works fine because I have very well written code, and the tests, we don't need this window anymore, and the tests just work fine. The program we are testing is the sum of squares program. So you give it a list and it just sums the squares of those numbers up. So for example, in this case, it would be 0 squared, 1 squared. The sum of that is 1. If you would add a 2 here as well, then we would have 5, because we would have 1 and 4 and 0. So it essentially just does that. So we can have a look. So yeah, it just iterates over the sequence, squares it, and sums everything up. And then we have a test function for that. So we have all these nice lists and the outputs we want to have, and we just test all of those. Okay. Now, one problem we have is it's wrong, it's broken. And we got a bug report that a certain configuration doesn't work. So someone said, yeah, I tried to run it with 100 and 1000, and your result is wrong. The result is 1 million, but it should be 1,010,000. So we add that as a test case to see if everything's fine, and maybe the problem is something else. And we run the test and we see, oh, yeah, indeed, this is wrong. So we go back to our code, we fix it, and we say, okay, let's try it. And we see, okay, now it works. That's pretty good. So now we can use Git, and here you can see that this editor also has an integration for that. It tells us, oh, you have this change, you have this change here, and we can add all these changes to our staging area. And we can say, okay, we fixed the 100, 1000 bug. Okay, so let's commit that and send this to the repository, and everything is fine. So now if we go back to our repository, we see this new commit here. We see that a pipeline is running. We can go to that pipeline, and it will take a few seconds. And I hope it, oh, now we can see it actually doesn't work in the pipeline. So for Python 3.5, it says it's failed. That's pretty cool, because we figured out, oh, we use a syntax feature here, these underscores, which are not available in Python 3.5 yet. They just became available in Python 3.6. So I didn't test that locally because I thought, yeah, it works on my machine, and so it should be working on your machine as well. But in fact, it doesn't. It only works on, oh, I'm in the wrong side. It only works on a machine which doesn't have Python 3.5, but a later version. So we have to remove the underscores again. We can stage our changes here. We can say, okay, remove underscores for Python 3.5. We can commit it, sync up our changes, so publish everything. And our new CI run, which is now in progress, will hopefully eventually say everything works. Let's see. Okay, it takes some time. There we go. And now it's also running on Python 3.5. Okay, so all this magic only because we set up some CI will help us to avoid these kinds of mistakes, because now we would know, okay, we shouldn't have pushed the other code into production because something was wrong there, but this version works now and we fixed our bugs. And it's much better to have that this way than to have Jane compiling it every day on all these 3 versions and testing everything. So that's much cooler. So did we solve the delivery for tomorrow? Yes, whenever our pipelines are done, we can say, okay, we could deliver this potentially now because everything is there. We still have the problem of versions. So we just saw that, okay, we can run something with Python version 3.5, Python version 3.6, 3.7, or something like that. But that's not always that easy. For example, if you would try to run something which is very old, or with Python 2, it's very difficult to install the outdated Python 2 on your next generation MacBook or something like that, because they just don't support it anymore. You sometimes might want to have a different tool or library which you can't really install twice. So have you ever tried to install, for example, Qt, a GUI library in 2 different versions? It's very difficult to get that right. Sometimes you have software which only runs on Windows or on Linux, or maybe even only on Macs. So it's also very difficult to get that right if you have the wrong environment. And if you deploy, for example, your website somewhere and you need a specific version of Fast API or Django or Flask or something like that, it will also be very difficult to get that on a server which, for example, is shared among others. So how can we ensure consistent environments in these cases? The easiest answer to that is, we just use Python virtual environments. But that doesn't really solve the problem with Qt or something like that. So you might use Conda environments, which come with Qt, for example, or with specific versions of TensorFlow or whatever you want. But another simple solution, and which is kind of a generic solution people in the industry currently use everywhere, are so-called containers. A container is essentially some process which isolates some system resources. So you can run a container and it will only be able to access some certain amount of memory, some CPU cycles, and it will only be able to access a certain set of files you allow it to use. The access to other resources, for example, some other files on your computer, or your GPU, if you don't specifically allow it, is simply forbidden. And we can start a container from an image. An image is essentially just an archive. So it's like you would package a tar file or a zip file, and you would put in all the libraries and tools you need. So for example, GCC 9, Qt 5.10, and maybe NumPy or whatever you want to have. You can put everything into the zip file, send it to your colleagues, and then they can essentially run a container, so a process which has exact access to exactly these files you put in there. Okay. One of the biggest advantages of containers right now is that almost all cloud services or scheduling services, so be it AWS, GCP, Microsoft Azure, or Slurm, or Nomad, or whatever, all these tools are able to run containers because containers are a so generic abstraction, which are so well defined that you can simply run them almost anywhere. So that's pretty cool because now you can essentially just package your software into a container or into an image, which you can then run as a container wherever you want. So let's see how this works in practice. So I have a very small Python script prepared. It's this one. It's very boring. It's just some print statements which claim to create some plots, and it's in Python 2 syntax. So for those who haven't worked with Python 2 in the past and grew up with Python 3, in Python 2 you don't need parentheses for this print statement, but in Python 3 this is a syntax error. So if we can close this one. So if we go to our script here and try to run it with Python 3, we will get a syntax error because we are missing the parentheses in the call to print. Okay, so there is an easy fix. We could add parentheses here, but sometimes Python 2 scripts are not that easy to fix, or sometimes you have a very specific version of NumPy and you simply can't fix your calling code because it would break everything down the line. So you still really want to run this with Python 2. Now this is where Docker comes into play. Docker is one of the biggest container, let's say, runtimes. So they offer you to run containers, and they offer you to share and download pre-packaged archives, these so-called images, from the Docker Hub. So here in this case, I just opened one of the images here on Docker Hub. We can see, okay, this is an image for Python with a version 2. And this image has some files in there. So this is essentially the operating system abstraction they put in there. And this would be the steps we had to perform to essentially get to a specific state in our working environment to be able to run whatever we want to run. So we have to do some updates and some installations of packages. We would have to set some environment variables, and so on and so forth before we can actually work with Python 2. So all of this is done already, and we only have to download this. We can do that with Docker pull, and then we just specify we want to have Python in version 2. And I already downloaded it yesterday, so it's pretty fast now, because it just checks, oh, do you have this version? Okay, you have it, so I don't have to download it. But if you wouldn't have it, it would now download it. It's about 300 megabytes or something, and then you would have a Python 2. Now, to run it, it's a little bit more difficult. So you would have to, and I already prepared this so that I don't make a mistake. So you have to tell it which resources it is allowed to access. In this case, we want to additionally allow to access the current working directory. Because if we wouldn't do that, and actually let's do that first, if we don't allow to use the current working directory, it will claim, oh, I can't open the create plots file because it's not there. But if we add this constraint, so this means use the print the current working directory. If we simply do this and say, okay, you can mount this directory, you have access to it now, then it will be able to find it and it can run it. So we only have to essentially pull a specific Python version and we can run it right away and use it for all our old dependencies. Now, in this case, that's pretty awesome in itself already, but we can take it one step further. Our create plots doesn't really need anything in any external input or something like that. It's very self-contained. So what we can do is we can build our own archive. If we build our own archive, we can then share it so other people can use it. So I already prepared something for that. So that's this Docker file. It's essentially what we just saw on the website. It's some instructions. In this case, we say, okay, use Python 2 and copy the create plots py we are using here into this archive. And then whenever someone uses this container, so runs the container from this image, then they should use this command. This command is essentially what we just did here. So it just says, okay, we want to run Python with create plots. Okay, I specified Python 2 here, but it's symlinked, so it will still work. And if we want to build that now, we can simply say, okay, Docker build, let's call it plotter, and we want to build our current directory. So we do that. It does some stuff here. Again, I did that yesterday already so that it's fast now. And now we can run our plotter. And we don't have to give it access to any other resources because the only file it needs is already in there. And now we could do it simple in a simple way, similar to what we did with Git. We could push this image, the plotter image, to some registry somewhere, so to the Docker Hub registry or wherever. And then our colleagues could pull it and also work on that. And if we would update it, they would also know, oh, you changed the plotter image, I have to get the new version, and then they can also run the new version. Okay. So that's essentially a way to abstract away all your dependencies so that you can run your software in an environment where you know it will have these properties. Okay, so now we solved all our problems. We solved the final problem with version control. We solved the version or the dependency versions with containers. And we solved the continuous delivery so that we can deliver whenever we need it using continuous integration and continuous deployment. That brings me to the conclusion. So you should always plan ahead like this. Using version control, you should always be doing that from day one on. It's very important to keep everything there, keep everything in check, and you can always build on top of it. So without version control, it would be very difficult to have this automatic testing and deploying. And without automatic testing and deploying, you would always have to build your containers yourself. But you can also have your CI do that for you so that you can sleep well, have a very good peace of mind, and you always know whenever something breaks, I can go back to whatever version I want to have. Thank you very much.
Thank you very much, Sebastian. That was a fantastic talk. A walkthrough from version control up to the containers, showing all the steps. There are a couple of questions in the question and answer box. So the first one is that I'm going to ask is from Sophie, that asks about the difficulty of set up a CI framework for a complete beginner, because most of the people working in academia are not familiar with these concepts. So if someone starts to do this today, is it difficult?
And that's a very good question. So originally, the idea with all these DevOps things was that all the developers will also become operators now. So we just give everything into the hands of the developers so that they can all do it on their own. And that's how it's supposed to be. So it shouldn't be too difficult to get something up and running. In fact, if we, now I closed this already, but if we check our demo here, oh, I'm not sharing anymore, right?
Yeah.
Okay. So if we check our demo here, to actually get these jobs with Python 3, 4, and so on to running, you only need a little YAML script which contains definitions for individual jobs. So you say, okay, I want to have the job test 3.5. I want to have an image. So that's in this GitLab CI YAML case, it's some Docker image, which we have seen before. Then this is a specific thing which just says use a computer which has a certain tag. So on this GitLab instance, all the runners have different tags. So this was just one I had to use now. And then you essentially have to write a script. So you just say, okay, we want to have a script, and this script is PyTest in this case. So whenever you can write a script to automate something, you can just say, I want to run this script here, and it should be run in an environment which is set up like this. So that's pretty straightforward. Of course, the devil lies in the details. So I would always recommend to at least try it out. If you have a GitLab instance, try GitLab CI. If you're working with GitHub, use GitHub Actions. If you have a Jenkins somewhere in your company or at your university, try to use that. They all have different configuration files, but the concepts are in general the same. So you always have to say, I want to have this kind of environment. I want to have, for example, here some requirements. I want to install, for example, PyTest or some other software. And then I want to run a script. And it's usually not much more than that. And if you, for example, want to have an archive at the end, then there is some command you can add here to say, I want to have a package built, and this package should be uploaded somewhere at the end. So it's really easy to get started, but of course the difficulties come with the details, and then it might be helpful to get to some more DevOps experienced person. It also depends a little bit on how much time you have for these kinds of things. So at Mavis, we have a team of DevOps. It's only a handful of people, but we are there to actually help our projects to set these things up because they usually simply don't have the time for that. But when I got into these things, that was usually just during my research, and I just decided, okay, I have to do this now automatically, and at the university, there's usually not that many people who can help you setting these things up. So you're lucky if you have a GitLab and they already set up a runner for that. So a computer which can essentially run these scripts. And then you're very often, unfortunately, on your own. But it's possible, and you should definitely try it out.
Yeah. Fantastic. I mean, something also related to this. So CI and CD always relies on some CI/CD server. So it's always a cloud service, right? And
it doesn't have to be a cloud service, but yeah, continue. Okay. Sorry.
Yeah, I was just going to ask, what are a couple of services that, what are a couple of tools that provide this service? So you mentioned GitHub and GitLab and Jenkins. Is Jenkins also open source and free, or is it paid?
It's definitely free. It's also, as far as I know, open source. It's a fork of Hudson, so you should be able to find it somewhere. Yeah.
Okay. So what are the other tools that people can use? Yes.
So the other tools for that. So there is some tools which are only for continuous integration and development. So for example, here in the case of GitLab, it also has all these repository management stuff and issues and so on. But there is, for example, I think it's called Drone.io, which is something you can self-host, and that's only for building. There is Python BuildBot, which is also a tool to simply build from some repository, so it's similar to Jenkins. And then we have some, let's say, cloud providers which focus on these testing things. There is Circle CI or Travis. Travis is a very huge one, and they also have some free tiers and a very good support for many different versions. And there is AppVeyor, which provides support for Windows CI. So one of the big issues you sometimes have is that you can only run Linux scripts, or so for example, Bash scripts in this case. But with AppVeyor, for example, you can also run Microsoft stuff. So you always have to take a look. I think for my master's thesis, I used Semaphore. So there are many tools for that. Yeah.
Great, fantastic. I also had a question regarding version control and Git.
Yeah.
So what I've seen in the academic environments usually is that people have some defense against going toward these tools, basically because they feel to be somehow complicated.
Yeah.
And most of the people are not, I mean, familiar with working in terminal, either it be Linux or the command line on Windows.
Yep.
So is it going to be necessarily on terminal, or are there GUI tools?
No. So you only need the terminal if you broke something and you really have to fix it and you have to go into the inner machinery of Git. I personally like to introduce it with a terminal because it gives you the idea of where it comes from, and that you have all these commands and they are not really that much magic. But there are lots of user interfaces for that. So we have seen it here in the Visual Studio Code already in my presentation, where it even shows you all your changes live, and you can just click on this little plus and say, okay, I want to add this to my commit. So that works. But there are also dedicated tools for that. So if you install Git on Windows, it will even ask you during the installation if you also want to install, I think it's called Git Desktop or something like that. So that's already a tool which shows you all the branches you have, all your commits. It allows you to sync up your work. They usually also come with editors for your diffs, so they will show you. I have a diff here. I have a change somewhere here. There is many tools. Yeah. And essentially, and that's the beauty about it, they all work together. So if you prefer one tool, you can use it. Your colleagues can use a different tool because the underlying thing is always these command line scripts. Yeah.
Great. Thank you. Also, one final question I had was regarding your career trajectory. So you said you're a DevOps specialist working at Mimes. So were you a researcher before that, or did you start as a software specialist from the beginning? So were you a researcher and then steered toward DevOps, or?
So before I started at Mavis, I was working as a researcher at the university. So after my master's, I worked for 3.5 years at the University of Bremen, and I was mostly working in everyday activities. So that was for robotics and making them understand natural language a little bit better. Yeah.
Cool, cool. It's just good to see that there are various career decisions that people can take after doing a research job, so that people may want to go toward more software engineering centered roles, such as a DevOps specialist. Thank you very much for your talk. That was very helpful for me, and I'm sure for many others.
Thank you very much.
So next on we have Martin here from Graz University of Technology in Austria, and Martin has been a pioneer in software engineering world in the MRI domain, at least, and he has lots of experience in developing the BART project. So he's going to talk more about that for us today. Floor is yours.
Thank you. Having me. Let me share my slide. Some luck. Oh, God.
Martin, is it not working? Oh, probably a technical issue with, yeah, but is going to be back soon. Yeah, okay, you're back now for me.
So I'm back. Yeah, so something is strange with me and MI together.
Yes,
the computer of the host crashed in my session, and now my browser crashed. I have no idea what's wrong, but let's see. Yeah, back in like in a moment. Hope it doesn't happen again. Okay, so. Start my slides. Share my screen again.
Yeah, oh, perfect.
Okay, now let's give it a new try. Okay, yeah, welcome everybody to my talk. My plan is to give you a bit of an introduction to BART and our experience developing the BART toolbox over the last 10 years. It's almost 10 years now. And so this is, I'm just going to tell you my opinions and what we've learned and how we do things. This may not always be what you have to do, or might also not be the right choices for your project or whatever you are planning to do. So there are many different ways to do things. Also, I have my own opinion sometimes about what's good, but I will try to give you a little bit of a background why we do things in the way we do it, and just so that you get also an impression how we do stuff in the BART project. So I will start a little bit, give some background about developing research software as open source software, which you all know is very challenging. And then I plan to go a little bit into BART for those who haven't seen it or know it. I will not give a full introduction, just some very basic ideas how it works. So if you want to learn more about that, we have a lot of webinars and tutorials about that. And then I want to talk about BART development, the programming language. So we develop it in C, which is explain why we do that. A bit about the tool chain, the version control. So we had a great talk about this already, but we use this in BART, continuous integration. At the end, then I will also want to go a bit about distribution, how we do releases, package, and maybe as an outlook a little bit about reproducible papers using BART, which is maybe an ongoing project we have. So open source projects in science, of course, we all know that science increasingly relies on advanced software to do our work. This is, especially in my area, image reconstruction, of course, an important topic. Also sequence programming, but many other things, post-processing. We rely on advanced software, and if we want to make it reproducible, then this also becomes like a community issue, how this software is developed and maintained. In science, of course, this is very challenging. So we have difficulty getting funding for software development. For BART, we now have a grant to do something, but it's still, in general, it's relatively difficult. So often it's developed as part of other scientific projects, which is, of course, not ideal because then you have different focus depending on the project, different research focus, different goals. You have a changing set of contributors, so students come and go, collaborators come and go, depending on the project, and maybe they work a little bit on BART and then they leave and do something else. So this makes it challenging to develop advanced software in this environment. Of course, we also usually work with non-professional programmers, postdoc students who do a project, and as part of this project, spend some time developing BART. And of course, sometimes it's just a little side project. Sometimes they add a lot more. I think Mavis is a big exception here. But at universities, we don't have this. There's, of course, the idea that universities should have professional programmers. developing research software, but at least currently that's not what I have at least available, and I don't see that changing. So I spend a lot of my personal time, and that is probably the critical resource then, my time and also the time of my postdocs and students, which they invest into BART, and which we also have to also do other research projects. So this is limited, and that also influences how we develop BART, why we do things in a certain way, why we don't do some things we would like to do otherwise if we had enough time. So the question is also, like, if you think about doing something like that, there are many reasons not to do it, right? So there are some reasons why maybe doing something like BART is actually not a good idea. So still in science, novelty and impact is valued more than reproducibility, sadly. So you invest a lot of time, but it's not like something, I wouldn't say it doesn't help publish papers, but certainly having some interesting or new result or method is more important to reviewers than that you actually develop some software. And then you make it available and make it freely available as we do, then people use it and they do great stuff, which is fine, but you don't have a direct benefit of it. You don't get co-authorship, you don't get, let's say, funding from their grants. So I know many people who develop software and then give it only to selected collaborators, and then they get a co-authorship, or maybe they then get a joint grant or something like that. For BART, that usually doesn't happen, right? The people take it, they do it, which is also great. That's why we do it, but it's something to take in mind, right? It's not that you get the same recognition from your users as if you keep it closed and have some selected collaborators you share your software with. Also, very few users contribute back. So that's might depend on the project you have. There might be a project where there's more users contribute back, but but it's not often the case, I would say. It's a common problem with open source projects. If they're really big, that works well, but for many others, it's a problem, or not a problem maybe, but it's something to keep in mind. So you cannot necessarily expect that a lot of the development is suddenly done by others, and you just have to merge it. We knew that from the beginning, so we talked to other open source projects at the beginning. Maybe Civic from UCSF, which is about spectroscopic imaging, was a great software package, or still is. And the developers also told us directly, it's great to do it in open source, but don't expect that the users will contribute a lot. But users will do other things. In particular, they will complain. So if they have problems, if they find it hard to work with, if the documentation is missing, which it is, right, then they will actually not be happy. And sometimes some users will complain about that, right? And that's also not always nice. On the other hand, it's not always the case that no users contribute back. We have a couple of users which contribute back bug reports or patches, and that's of course really great. And thank you to all of you who contribute back, even if it's just a well-explained bug report, which gives us a lot of information, which helps us fix some problem also. Now that's maybe a bit pessimistic. There are also, of course, many good reasons to develop open source research software, even in a scientific environment where it has to be done on the side. It helps, of course, with reproducible research to have this open source software. That was one of the main motivation. it preserves knowledge in a very good way. And that's true also inside a lab. Like if my students do a project with BART and integrate some new features, then usually we can rely on it working even later. We can have a follow-up project and someone can directly build on top of this work. If this was a separate project, the student did and maybe does everything right and puts it into GitLab, but still he goes away and he's the only one who worked it. Often these side projects then die and the knowledge how to use it is lost, and someone else might not want to start with that at that point, but start from scratch or something. With BART, that works very well, so we can really build on top of each other and have one new PhD student coming in, he can directly start at a point where somebody else stopped. So this is really useful, and also, of course, outside of the lab, people can use our the know-how basically which went into BART. So it enables more advanced research also, because we have a lot of advanced methods implemented and you can directly use them. And if you would have to develop that from scratch, often you wouldn't do it, but because it's available, you can push forward into maybe something else, something new, just building on what's already there. And finally, of course, for me, it's also something which is a lot of fun. I like writing code, developing software. It's certainly a lot more fun than writing papers for me. And especially a lot of papers don't have so much impact maybe. But if it's a good paper, it's of course also a very nice contribution. But I think in science we have too many papers which actually don't contribute enough, and that might also be frustrating if you write a paper and nobody reads it or uses it. So that's different with software. If you have software and it's useful, people will actually start to use it, and it's a real contribution which helps other people. So that's why I think it still was for me the right choice to actually do that project. So what is BART? For those who haven't seen it or know too much about it, we started it 10 years ago when I went to Berkeley to Mickey Lustig's lab. The goals were to have something to do rapid prototyping of new techniques in image reconstruction, in particular compressed sensing and parallel imaging. Reproducible research was a clear goal from the outset. To be able to give it to others and allow them to reproduce what we did, what we do. And another goal was to have something which at the same time is good enough that we can actually move it into the clinical environment and actually use it for image reconstruction there. So we did a lot of studies using software built on top of BART, which is used then to show that, for example, compressed sensing type reconstruction can help in certain MRI scenarios. Nowadays, it's a development just done collaboratively by different sides, mostly by my group now in Graz, and my former group, or still my group, which I still have in Göttingen, together with Mickey Lustig's group at Berkeley and John Tamia's group in Austin. BART is freely available. We picked a license which makes it free to use, also for commercial use. That's, of course, something you need to think about when doing an open source project. Just to mention, I mentioned getting funding for software development is hard, and for a long time we didn't have any, but we now have a dedicated NIH technology dissemination grant, which allows us to do certain stuff. So I'm very happy that we finally achieved it. Yeah, we have it for a while now, but that took quite a while. So what can you do with BART? And just give some examples. So we have this PIX tool for parallel imaging compressed sensing. which is very flexible and generic and can do parallel imaging, compressed sensing, non-Cartesian MRI. It can use multiple regularization terms. It can use different types of regularization, which we use in. It can process arbitrarily high dimensions, and so on and so on. So it's like a Swiss Army knife for image reconstruction, I would say. So this is a very powerful tool, and of course it has a lot of flexibility and features, but this also is of course challenging then to develop and to maintain so that everything keeps running, keeps working, even if you like add new functionality or change the algorithms to make it more efficient or something like that. So software testing will also be a big topic, or is a big topic for us. Recently, we added machine learning techniques. That's work done by Moritz Blumenthal in my lab. He actually extended BART to integrate a lot of these machine learning techniques. We started with this variation network and model and showed that we can implement it. And a lot of people ask us why not just use TensorFlow or PyTorch. And so we decided to put it into BART. Maybe it becomes a bit more clear later why we do it. But one reason is also we could, and that's certainly fun to implement this stuff also on your own. And it turns out it's also not competitive, so it's not impossible to compete with these commercial, or not commercial, they're also open source product, but driven by big companies like Google and Facebook, because essentially you can build on underlying libraries which have all the important core mathematics highly accelerated. So we can easily, or not easily, it's still a lot of work, but we can actually build on top of these libraries frameworks which have a similar efficiency as these other deep learning toolboxes. If you develop such a toolbox like BART, then one big part of it is also how to basically present it to the community, how to make it available, how to allow people to use this and contribute. Jump out of my presentation and show some of these, discuss some of these things. Let me start a browser here. If we go to the website, well, let's go first to the BART repository. We put it on GitHub. You can see here our, maybe I need to make that bigger. Our BART repository, we have this MRI recon group where we have many other repositories, and we'll show some of them later. But this is the one for BART, and one important point is that we have a README which describes a little bit, points to the website. We then have, and we have some information for contributors, which also clarifies some legal aspects, that basically expect the contribution to have the same free license. So this is some precaution that to avoid that people naively commit code which they don't own, and all this stuff has happened for other projects, and in some cases also to BART. And then, of course, that's something we need to avoid. So and it's good to point this out to make this explicit. The license is also something we have in the repository. We picked a BSD license, which is also has historical reasons, because it was started at Berkeley, and that was one of the licenses they knew and allowed us to use. So there are many other good licenses to choose from, and I think we had tutorials before how to pick a good license, or you can find something on the internet. But it's something to think about, especially if you start up a project, how to do that. We have then the website, which provides more materials. It gives a background about what is BART, give some initial impression how it works. We have then tutorials and webinars. We list some features which we have so that people get an idea what it potentially could do. We have a mailing list just posted in Berkeley where people can ask questions or communicate, and this is very helpful because often I get personal emails and I don't have the time anymore to answer all of them, or it takes a long time for me to come back to it. So if people send to the mailing list, then often other users or other BART developers can help with these questions. And sometimes we just send an interesting email because I tried to convince ChatGPT to use BART, and I report my experience here. More often it's more like discussions about people using features of BART, how to use something, like discussing about stack of stars or eSpirit or other stuff. So it's really important to have some forum for communication. I like email because it's accessible to everybody. You can archive it so people can go back and look up what was discussed. There are, of course, other possibilities you could use. Right. What else did I want to stop? So how to contribute? You need some information, the website, the mailing list. So let's go one step further. I want to show you a little bit how BART actually works, like how it's composed, what tools, how these basic tools work. And if you want to follow along, I will just start one of the basic online Jupyter notebooks we have. So if you go back, maybe it's best to go in the BART repository, which is on GitHub. And if you go to this MRI Recon group, so one level to the top, there's this BART binder repository. And if you go there, there's different ways to directly open BART in your browser. So that's very nice for little things, to show people how it works and also do little MRI experiments. It's not ideal for big computational stuff that we usually do locally. So I want to point, before going into these repositories, I want to point a little bit out that what's happening under the hood here. We heard about Docker before, Docker containers. So this binder on Google Colab essentially are also Linux container, Linux environments, which then run in the cloud and which you can use. And these can be constructed or called directly from a GitHub repository like this one. And then they need to be configured to be able to use BART. And in BART, that turns out to be relatively simple. For example, for binder, you can just tell it to install BART, and it will know how to do that. Something I will come back at the end of my talk, why this is so easy. And then we can, in some other script, basically set up a bash kernel for Jupyter so that you can interact with that. So this will install like a BART package from a Linux repository, so it's not always the newest one. If you want to go to some newest BART version, you basically have to compile BART in this container environment, but also this can be done. So then you have to install some other packages. And then call a script which actually unpacks, downloads the BART source code from GitHub and builds it inside the container. But also that's relatively simple and relatively quick. So that's what's going under the hood. If you do that, and then inside this repository we have, let's go back to to this branch. We have these Jupyter notebooks which you can start. We provided links here, so I suggest you either go to Google Colab, which has more computational power. Okay, and then But I think you need a Google account to do that. So if you have that, you can try that. I will start that. Alternatively, you could also go to this launch binder, which is free. You don't need an account, but it's a bit more computationally limited, and you will also not see some of the steps I'm doing, but should be also nice to follow along. So if I go into the Google Colab, so the binder will maybe take a little longer to start up. For me, it's already running, but I don't know. Then what you can do in this Google Colab, you basically have a Linux environment, and that's very similar to a command line. So I always wonder why people are scared about the command line. It's not much different than actually typing things into a Jupyter Notebook or MATLAB. You type commands and stuff happens. So please don't be scared of command line stuff. I would say it's a really useful thing to know, and to efficient way to interact with the computer. So the first thing we can do is install some dependencies which we need to compile BART, to build BART from source code. Could also install BART directly, but then we would get an older version. It's useful to know how to do that with a new version. It has very few dependencies. And I will come back to this a bit later, why I think that's interesting. If we execute the cell that will install these packages, then we can actually check out from Git in this notebook the BART source code. We'll now check out the specific version here, and then start go into the BART directory and start the compilation with this command. And all this works exactly how you would do it on the command line, but now basically run it inside this Google Colab environment. Compilation now takes a couple of seconds. It doesn't take too long. Afterwards, we will set up some Python environment. So this is maybe one of the advantages of these environments, that you can mix it easily, the shell and the Python. So we will mostly use it to show images, which can be done nicely using Python. So this will come after the compilation, which is now still ongoing. And then we wait a little bit until it finishes. So maybe in the meantime, I explain a little bit about why you will not see that usually done in the same way for other software. So usually software is much more, has much more dependencies, is much more complicated than BART. Often takes very long to compile. You would need a lot of special packages which are not directly available in Linux repositories. So BART is, for variety reasons, designed in a way that it has very few dependencies, that is simple to compile. So you can just install the packages on basically any Linux environment, and with one command compile BART, and now it's already done. So it really also doesn't take a long time. For a big C++ project, that may easily take hours. So BART is very lightweight in that sense. We set up some Python environment on that. We can then check that everything is done correctly, that we got the correct BART version that's actually running. We also set up a function in Python to show images. And then we can go directly into BART commands. And just for those who haven't seen that, BART are based on shell commands in this environment. With these exclamation mark, I can run terminal commands. Now BART would have different commands, like a command to create a trajectory, which has some options, like how many radial spokes, that it's a radial trajectory, that we want to use oversampling and stuff like that. And we can just run it. So if you want to have more details what this means and how it works, you need to go to one of our webinars or watch one of our tutorials. Then it has tools, for example, to simulate case-based data, like this Phantom tool, which now could take the case-based trajectory and simulate some case-base. The output are always files, right? So also in that sense, it's very simple-minded. Create a header file and a data file. And if you look at the header file, it is just a little text file which tells us the dimensions of our multidimensional array we got out. In that sense, it's also similar to MATLAB or NumPy. It tells us what command was used to generate this file. So this is something we basically added to improve our workflow to make it more reproducible, so you can easily play around, use BART commands to do some reconstruction, and later in the header we can look up how it actually was done and reconstruct and redo everything and put it into a nice script. For the same reason, we put in the version, so we know exactly what BART version was used. So if you want later want back and get a different result with the new version, we can check, okay, maybe something changed in between. We get a list of input-output files. Also, this is meant for making this reproducible if you look at these headers. Then we have more other basic tools, like in this case, we could do an FFT. Actually, I want to do that only along the first dimension. To get a sinogram, which we can now image using, for example, Python image view command. Also very easily, we can use a root sum of squares command to now compute something like the Ramlak filter from a radial trajectory and apply it to our case base. So we have an fmac command which multiplies. And then we have more advanced stuff like the non-uniform FFT and a joint non-UFFT, which would now take the trajectory, the case base, which is weighted by the Ramlak filter to produce an image. And this is just a very simple example how you can actually compose little tools to do something interesting. Of course, we have much more advanced tools for complex sensing, color imaging, and much more. But you get the idea. The philosophy is a little bit to have tools which do one job, and you can then combine these in a very flexible way to actually construct much more advanced reconstruction pipelines, which go from case-base to some pre-processing, some calibration, and then produce an image, or you can combine this with simulations. Now, this is what I wanted to show you about how BART actually works, but this is not the main part of this talk. I want to leave that notebook. Let's go back to my slides. So the next step is actually what I want to tell you is how BART is developed. This, of course, somehow influences what BART is and how it works. One of the core philosophies is to have reusable software components. So this is already something what you just saw in this Jupyter notebook, that we split things up into small tools which can be combined. And this is on the one hand, of course, a feature to make it more powerful to use, because you can combine things in different and new ways to achieve new things. But it's also for developing a useful feature, because we can test and develop things as components. So we basically reduce the complexity of the overall project by working in this way. At the same time, we tried that each component is as generic as possible. For example, that it can process multiple dimensions, that it has no arbitrary restrictions. Again, that makes it more useful, and by making these like on one hand, conceptually simple tools, but which are at the same time very generic and powerful. We can reduce the complexity of the project. And this makes it possible to actually also develop this, let's say, with relatively few resources. I already mentioned that we have a few dependencies. I think that's also something which is important, or at least we found it important. BART depends on relatively few external libraries, mostly something like the FFTW to do efficient FFTs, or BLAS, or LAPAC for linear algebra. And then, of course, we have a lot of optional libraries, like to use a GPU, CUDA libraries, or to make things faster. But the core set of libraries is relatively limited. And this we found relatively helpful for two reasons. One reason is that more independent from changes in all these libraries. So these are very stable libraries, and we expect things that after years it still works in the same way, reliable, that these are still well supported. If you think about Python, maybe as a counterexample, that's a completely different world where you have a lot of libraries available, and it has all the advantages. You can quickly get up and running, do nice plots and stuff like that. But also everything changes much faster, and you cannot often not rely that things work identically in the same way, even after short years. If you think back about Python 2 and 3, where a lot of Python code basically stopped working, or still works if you go back to all Python versions, but it didn't really works with new Pythons, then that is a problem, and it costs your time. And if you're a PhD student, you might not worry about it, but if you worry about the long-term perspective of your software, and you don't have a lot of time, then you don't want to deal with all these changes in your dependencies. And minimizing the changes then saves you a lot of time. Another reason is that it makes it more easily to deploy BART in different environments. So we don't rely on Docker usually. I mean, it's easy to create a Docker container also with a specific BART version. But as you've seen, that's not really necessary. You can install BART from Linux packages, or you can easily compile it in yourself in a command line, or in a Google Colab document. This also works because it has so few dependencies. So when you want to get BART running on a supercomputer, and there's a very old version of Linux installed, and then if you use more recent libraries, you may have run into problems. But usually we found it relatively easy then to still get BART to work. Backwards compatibility is important to us, so we try to not break stuff too much. Of course, we also want to implement new features. We want to fix bugs once we find them. Sometimes we will also change things because we think we need to do that to make things better. But overall, we still aim to not break all scripts, or at least find a way to support all projects which are based on top of BART. To also maintain that in the long run, so that things keep running and working as expected, we do a lot of testing, also that the results stay the same, at least then that's expected. If there's no bug, then we expect that the output of our reconstruction should not change. And all this we try to do with software testing, as we've seen also in the previous talk. So one question I often get is why BART is developed in C, and that has a different reason. Maybe the most important one is that I like C and know it very well. So it's also, for me, a very efficient way to develop software. So that might be different for you. But other reasons are that C itself is very stable. It changes very slowly. So old C code from 30 years ago still works fine today. So this is in contrast to other languages which develop more rapidly and sometimes also break backwards compatibility. And if you have a long-term perspective for your project, that's something to keep in mind. These are also relatively efficient. You can implement fast software with that. You don't have a huge overhead. It has static typing, so it's not a dynamically typed language, which I think helps also with larger projects. They are portable. It runs on different types of systems and devices, even other processor architectures. It has a very major tool chain. The compilers and debuggers are very good and also available basically everywhere and are generally of high quality. It's also conceptually relatively simple. I would say it's certainly not as easy as Python to get into, but it's still not a complicated language. If you compare it, for example, with C++, where you basically need to be nowadays an IT expert to really exploit all its features. So C is still much easier. Of course, there are downsides. So most students don't learn it anymore. So if they see a C project, they are not immediately comfortable with doing something with that. It also needs some time to learn. You're not as quickly productive as in Python, where you relatively quickly get started and also have quick access to a lot of libraries which allow you to plot stuff and similar things. In C, you need a bit of a time to learn how to do stuff and also what libraries you could use to achieve your goals. Still, I want to go now a little bit more again in the command line and show you some of the stuffs, how we do it, and just to give you an idea. Let's open that one. Terminal. Make that bigger. So I like to use in the command line, and I can just tell everybody it's a very efficient way to work with the computer, and it's not much different than using something like a Jupyter Notebook or MATLAB. I just can recommend to do that. And we usually have BART in library. That's now a Git repository, as we've seen before, so you can look at the history and stuff like that, and everything is here. But I want to go out now and just create a very simple C project just to see that it's also not very difficult. So we can start, and let's say we want to write a C program. I use this YE editor, maybe not the one which is also easy to use. So you should probably use something else. But we can write a function in C as easily as anything else. Let's output some stuff. So it's also not a difficult language, I would say. It has some time to get in, but we can just relatively quickly also create a complete C program. And then if you have a compiler install, which is also just available everywhere on a Linux as a package, also of course on a Windows, you can use a compiler then to compile your C program, and then if you call it, it will give you some output. So it's also not too scary or difficult to get into this, right? You would just need to learn the language, and then the problem a little bit is that in C, like in mathematics, you basically start with a blank page, and then you need to find a way to step forward. And this may be easier in Python, where you have all the libraries available, but in C, you basically have to find your own way. But for BART, essentially, if I now go back, BART is composed of such C programs, and we basically created a little bit of an environment which is similar to Python with NumPy or something like that, where we have tools now to load arrays from files to do processing. So if you go into the BART FFT command. It's just a little C command. It has a bit more complex. It defines input, outputs. All this is now using some kind of BART infrastructure, which of course you would need to learn a little bit. But then it uses like a simple C functions to do the FFT, to load files and stuff like that. So in BART, we have a lot of infrastructure to make programming very quick, so that you have also access to a lot of functionality very similar to NumPy in Python. But let's go back to our C program. We usually use so-called makefile, which tells us how to build this program, how to run the compiler to build it. So if I want to create typically what's called a make rule, which calls the compiler, defines the output and the input C file. I can tell it that this depends on the C file, and that is some really useful thing to do with these makefiles, because they automatically figure out if something changes in your source code, that the program needs to be recompiled. And if you have such a makefile, you can use make, which is another program you can install, and it will invoke the compiler for you and create the C program, which you can then call. And we also use that for testing. So we build make rules which do some tests, for example, which could depend on the existence of this tool, and then actually calls this tool. If I now run, you show that a bit longer, so the test goal would depend on the existence of the tool I just created. And if I now run this test, it would compile my program if it doesn't exist, and then run this program. And if it, because I made it in a way that it gives a good access code, which tells that everything is okay, it will actually be also a successful test. And so now if I have such a little infrastructure, that's all you need to get started, right? And basically BART started in that way. You can actually integrate this into a Git repository, just as we see in the last part. Complain a little bit about something, but I can just add these files I just created and committed to a Git repository. And then, as we've seen in the last talk, we actually have this under version control and can see all changes. If you look at the log file, you can see what I just picked, so you can go back in history. And now, if I want to release something like that to the world, I could go, for example, to a site like GitHub. That's also just what we did in BART. Let's find the right browser. Go to our MI Recon group. Essentially, I could say here, new. I want to have my new test repository, and I just create this. It is a public repository, and it will create it for you, and it will give you even instructions now if you want to go from the command from the repository, create it locally, how to basically push that to this GitHub repository. So I can now tell it basically that this should live at GitHub at this position, this repository. I think I want to rename my branch, and then I can actually push this to GitHub. And it doesn't work because I didn't set up something, I don't know. Doesn't like my public key. Why is that? It's good that I tested it yesterday and it worked. Yeah, never mind. I'll not have the time to fix this now. So you basically set up your SSH key on GitHub and then it's supposed to work. Anyhow, once you do it, you get a repository in GitHub, which now is populated with your files, and we can just go to BART. Now this is something you do. And if you have something you want to release on the world, this is something I also want to show you. You could go to this text folder. You can under Git create text, but then here on GitHub you also can create something what they call releases. Just sometimes you can base it on existing text, but you can then define something like a name for the release, describe your changes. So we always go back in the Git history and collect all the changes we did since the last release. So Git log can be used to give you that, and then we write a little bit of a change log to give the user the idea what's new in this version. So under GitHub, you can easily edit these files and design it. And then basically, once you have that, you can basically publish these releases and get something which then also creates zip files for users to download. So if you don't want to directly clone the repositories, you could also then download this release directly. And there's something you can set up, which is I found also is very nice. And you may wonder where this story comes from. So GitHub has an interface to Zenodo. Zenodo is a website based in CERN, which stores data for you. And basically, once you create a release on GitHub, you can configure it in a way that it automatically also creates an upload to Zenodo. And we do that with BART. It basically creates a zip file from the folder in Git and uploads it to Zenodo. And everything then is contained in this zip file for this BART release. And you could then also change the metadata, the authors, and stuff like that. And what's in particular interesting is that you also get a DOI for this BART version. And I like that because it makes it possible to cite this release in scientific publication. So otherwise, people would give a link to GitHub. And I'm not entirely sure that this will stay up forever. Maybe we would change opinion and use another service. Or Microsoft, which is the owner of GitHub, decides to ask for a fee or change the conditions in a way we don't like. So I'm not sure that GitHub links will work forever. So it's nice to also have a DOI for releases so that later, if you cite them this DOI instead, you can always get back to this specific BART version and to reproduce the results. Okay, so this is the command line make git. I just also want to show you quickly, if you go to BART, that also from the command line you can integrate with Python very easily because it's based on these tools. So for example, I can use the startup code to go into Python, and again, it doesn't work because I forgot to set it up. Set it up on the shell first, and then I go into Python, and then I could call the a BART command like this using our Python interface, for example, the version command, which now should give you the exact BART version. So making it a set of tools also makes it easy to integrate into Python and MATLAB. So that's actually how most of our users actually use it. And one final thing, maybe, which I want to show here, we write this unit tests as well. If they've seen the make file, which was often just make rules, which we run and run a little program which returns a positive error value as well, okay value if it's okay, if everything is fine, and an error code if it's wrong. And this is also not just for continuous integration, which we also do, and show that in a moment. But we also do that to find bugs later, it's very useful. And I created an example repository here with some commits. And at some point, I introduced a bug. Of course, here I did it intentionally. Usually, it's not by accident. Now, if I later want to find out where the bug is, I can basically exploit the fact that I have a thing in version control to automatically find this bug. And there's this bit bisect command, which is extremely valuable for that, because you can basically say, start a process, can tell it that, okay, the current version I run now, we just run this tool or this test, that it fails. So the test I wrote, on which I now call using make, is not working correctly. And can tell Git basically that this commit I now have is bad because the test fails. And at the same time, I now can go back, let's say for the beginning of this project, and say, okay, now at this time I think it was still right. So I tell it that this commit is good. And then Git will automatically check out and commit in between. And now you could run the test again. And it says, okay, I compile my tool, it runs a test, it figures out that it works at this time. So I tell Git that now this is good. And it will give you another commit to test. And just do the same thing. Okay, I figure out it fails. And then basically tell it that it's bad, and now it ends up and tells you basically the exact commit where the test started to fail. And this is extremely useful if a user finds a bug. You create a test basically which tests if the bug is there or not, and then you can basically automatically find the exact point in your history, which might be hundreds of commits where this bug was introduced. So this is also something we use a lot and is extremely useful. And then, of course, we also put things under version control and run automatic tests. Basically, we have this for GitHub, these files which define all the tests we run on GitHub. So if you go back now to our BART repository, let's see where we have it. Maybe I'll go back here. Oh no, I have to go. I'm icon BART. Then you can see here this green checkbox. And if I click on it, I just see that the automatic tests we've defined, which we all implemented in our make file, are automatically run and everything is good. And then we get this green checkbox, and we know that hopefully we didn't break much. We also run a local GitHub runner in our local GitLab, which, because my browser crashed, I'm also not going to show you also most of the time, but we also run tests locally, which is useful if you want to run tests which need a GPU, which we cannot do on GitHub. Okay, that's almost the end. Just quickly, what do we do for releases? I already covered that, that we make a release on GitHub with a changelog and then upload stuff to Zenodo, where we get a DOI, which is useful then for citing the specific release data. And then we make an announcement to our mailing list, also explaining the new features. And then finally, one step, and this is the last short thing I want to cover. We also create then packages for Linux distribution, in particular for Debian. And these packages also end up in Ubuntu. And that makes it also very easy to install BART. If you don't need the newest version, you can just install a package on Linux and using apt-get install BART, for example. And this is something which is based on a collaboration with the Debian Med project. So people who package software for medical purposes or biomedical research also in Debian. And there are a couple of links. So if you go to this page, for example, or you can also Google that, then or code from our website. Yeah, then you find information about this backend package. So in the Debian stable version, it's still an older BART version. If you go to newer Debian, you could get an up-to-date BART version. And this also comes with a lot of information. You can go to the developer information, which then has logs, which tells you that this was compiled also on different computer architectures. So it also runs on completely different systems. Or you can go in the continuous integration. So Debian also runs a continuous integration framework with tests, and we can see everything is fine and like that. Okay, we also have some packages for CentOS and Arch. I can't tell you more about that. That's some student of mine who did this. I'm not expert on that. So this is also something we do to make it more widely available and also more robust, because in that way it also gets a lot more testing. Okay, and the final thing, I'm not going into that more because we run out of time. This is something also which is ongoing. Now with BART, the problem is that the research we do is very computationally intense. So often we run hours of recons on a GPU. So we cannot, and often on gigabytes of data, so we cannot just package it in a zip file and give it to our papers. And it would also not be too useful. So the goal for us is that actually all this stuff we produce, all the old papers still work with newer BART versions, so that there's a long-term development and integration of our research in a way that it is more useful than just going back to a specific version and run the specific code for one paper again. But instead, we aim that even using new BART version, you could also run our old papers or do our old stuff and then pick up directly there and continue with the research. The challenges are the higher runtime. Challenges we encountered are also numerical issues. If library changes, or even processors change, then the numerical results may change a little bit. So you need to fix the tolerance, how good you want to be with reproducible. Ideally, of course, you want to have it deterministic, that it's bitwise identical. GPUs use is a problem because you need to check on GPUs. And then, of course, if you fix a bug, all stuff may change, and then often we need to implement a backwards compatibility workaround. And we work on that a lot at the moment. And basically how we do is we have for each of the papers, you go back into MRI recon again, a repository, and we started, let's go back, for example, to migrate-to-one mapping, which is one of our papers. We started to put, of course, we have scripts which run the code and produce the results of the paper using BART, which is not included in this repository. But then we collect metadata, which tells us which BART version is considered a reference for this paper, and then can use it automatically, compare results from this version, for example, to newer versions. We give it a canonical name for this project, a list of files, of scripts to run, and a list of output files and stuff like that. So this is something we're currently working on, and it's a bit of an outlook where we want to go with that BART project in terms of reproducible research. And with this, I want to thank you for your attention, and I overdid my time. My apologies, but if there are questions, maybe I have a very short time.
Amazing. Thank you, Martin, for the great tour de force into what you do to develop and maintain BART, and and the tools that you use to do this. There are, of course, lots of questions from Sophie, from Paul, and also from me, but we don't have time to do all of them. But let's see if you can answer a couple of them. So I think one of the important ones that comes from Paul is that what you're doing is to developing a software package in the academic environment. So how do you reconcile the need to develop and maintain a large existing code base with the desire of new students that want to use new or fancy languages other than C? Yeah, that could be a problem, I think. Yeah.
That's a bit of a conflict, of course, that people sometimes don't want to use C. It's not that a problem, as most of my PhD students then turn out to be happy with that and don't need much convincing. For like undergraduate students or smaller projects, it sometimes doesn't make sense because it would be too much overhead for a student to learn. So we also do a lot of projects in Python, and that could be often also smaller project built on top of BART or also separate. So we don't exclusively use C, but the experience is, of course, that the projects which go into C are the one which have the most impact for us, because then it gets integrated into the workflow, it gets tested, and then it has a long-term, it's very useful in the long run for us, and because other people build up on that. And that works sometimes also for Python projects, but much less so in my experience. Often these projects die at some point, or they just get archived, and they are there. You could reproduce it, but it's not like has no long-term impact for us.
Perfect. So one question which is also related to this that I was wondering, so there are lots of features and tools for construction that are in BART. So how do you decide on the many new tools that are getting out every day, which ones to include in BART and implement in BART? What's the decision process in that regard?
It's mostly driven by my own research. So I don't have time to implement whatever I want, right? So even if I think something would be nice to have, I usually don't be able to implement it. I only can implement it if I have a project where then somebody can work on it. Sometimes I implement stuff on my own time for fun, but that's then just smaller stuff. If I have some spare time, think it would be nice to have it. But otherwise, it's just my own research also decides what gets developed for BART. Funding.
Yeah. So one last question, which is also related to this, that Sophie asked. So if you want to overcome this issue and everyone would like to contribute to the BART project, what are the reasons that people you think are hesitant to do that, and how can it be made more easily?
I don't know. I mean, one reason is certainly that it's not as accessible as a Python project to go and see, and that I think many people, especially in our field, and students don't learn in C anymore, and so they learn Python. And then they look at our code, it looks complicated, and then they are scared and even don't consider that they could usefully contribute. So that's a bit of a tough problem, because I think we would need to offer some training for people to get into it. And I think if you had the training, you would figure out that it's not actually that hard to go into it, but without having that training, it might be just too hard for some people. But otherwise, I'm also not sure. There's also not a lot of motivation for people to contribute back. I contribute to other open source projects like GCC or and it's often a lot of work and a lot of back and forth, and the people help me. So it's also sometimes you have to. I mean, you cannot just contribute easily or something. It's also work, right? And when I can understand if people then say, okay, my time, I do something else. Yeah.
But I think there are also times that when a PhD student, for example, wants to contribute to a project, they usually seem to think that I am not qualified enough to contribute to this. I'm not qualified enough to make a pull request or something like that. So is it the case with BART too? So do you have high bar for contribution?
Yeah, I mean, I try to be open because we don't get much contribution, then I try to help so that it goes in the end. But of course, at some point you have to be able to say no or even remove stuff again, because in the end, the criterion for me is if it takes too much time for me, I just cannot do it. We had that, for example, with CMake. People didn't like our make file, so they want to use CMake, and they contributed a CMake which was hundreds of lines of code and was probably good. But then they went away, and it has missing features and problems, and I couldn't change it because I didn't understand it. And so at the end, I removed it again, right? So, but I don't really have a choice, right? And for software, for code, it would be of course similar. I needs to also needs to work and be good enough. It needs to be maintainable. So I could not just merge everything, right? But the point is that I think if you want to contribute, the best way is to talk to us and really start also collaborating more directly, and then that would be a way forward, because then we can look at it at an early time, give some advice early, and then I could go step by step.
Perfect. Thank you very much for your talk and the discussion. There are a couple of other questions from me on the Q&A box, but probably you can put some comments if you feel like on them.
Put some comments in. Yeah, thank you.
Yeah, thank you.
Yeah.
So, sorry, we ran a bit out of time, but next up we have Paul from Oxford University. Paul is one of the main developers of the FSL package, which is, I think, most of the people working in MRI are familiar with. So the floor is yours, Paul. Go ahead. I can't hear you. I still can't hear you. So yeah, you have no sound. Probably you want to refresh your tab or close the browser window. I heard something. No. Yeah, he had to probably close the window and come back again. So yeah. Maybe we can continue with the questions with Martin.
Okay.
Yeah, I had a couple of practical questions. So in developing BART, for example, which is a good example of software package in the academic world. So is it difficult to get funding for it? Do you have separate funding for it, or is it part of your own funding?
We have funding for it now. For a long time we didn't. Maybe.
Yeah. Can you test it, Paul? No, we don't have your voice. Yeah. Also, yeah, and in the bottom right, there's a gear window. If you
Yeah, I've tried
go.
I literally chose an option that I'd already chosen before. Sorry.
Good.
Sorry.
You can go ahead with you.
Okay. Should we get started then?
Yeah.
Okay. Oh, and I think Martin's screen needs to be unshared.
Yeah.
I can share mine. Okay. Let's try now. So, okay. Hopefully everybody can see my screen. And I guess we can get started. So yeah, thanks, Mo. Hi everybody, my name's Paul, and I'm based at the University of Oxford in the UK. And first of all, I'd just like to thank the MRI Together organisers for putting this event together and inviting me to give this talk. I feel like it's quite a privilege to be able to talk today. And just very briefly, a little bit about myself. I'm a software engineer at the Wellcome Center for Integrative Neuroimaging, formerly known as FEMRIB, and I spend most of my time working on the FSL software library, which is a software package for analysis of MRI and fMRI and diffusion weighted data. I'm the developer and maintainer of Fossilize, which is an MRI image viewer. And although in the past few years, I've been spending a lot more time working on the core FSL code base, trying to modernize it, the code itself, and in particular, the development practices to bring it up to more modern standards. And in this talk, I'm basically going to try and convince you that you should probably be testing your software a lot more than you are doing at the moment. And my talk is going to be structured as follows. I'm going to start off by convincing you that, or trying to convince you that testing is necessary. Then I'm going to introduce a few basic rules or guiding principles in software development, which you can apply in your own work to help you reduce the number of mistakes that you make and bugs that you introduce into your code when writing software. I'm then going to focus a little bit specifically on testing Python applications. This talk is somewhat biased towards Python, as this is the language that I've spent most of my time working in over the past 8 or so years. And then I'm going to finish off by giving a quick demonstration to show you how easy it is to have your tests automatically executed using GitHub Actions. And we've already seen some of this in the previous 2 talks. So there's a nice continuation. And so I'm going to start by making a claim that the vast majority of scientific research results published today and over the past few decades have been generated using some kind of software. It's kind of obvious, I suppose, if you think about it. But I would also wager that a large proportion of these results have been generated using custom or bespoke software scripts written by the researchers themselves, or possibly some poor, unwitting graduate student. And it's these research results, along with our own custom software, that we are all building upon to generate our own research results. So we're placing an enormous amount of trust in both the commercial and freely available software packages that we use and the custom software scripts that we or our students or colleagues have written. And I think there's a bit of a problem in having such blind faith in the software that we're using, because there's often a stark difference in the ways in which research quality code is developed when compared to commercial or industrial quality code. In an industrial or commercial setting, software is often created according to a much more rigorous development methodology where a lot of emphasis is placed on planning and designing the code base, and the level of testing required is much more stringent. Whereas in a research setting, software is created in a much more organic or ad hoc manner. And there are a range of reasons as to why this is the case. Private companies often have a lot more resources, funding, than academic and research institutions. So they're able to dedicate more people to each aspect of this software development process. For example, in in a commercial setting, a test engineer is a full-time role, whereas that's unheard of in a research environment. And in certain sectors, such as in production of medical devices, companies developing commercial products are often working at a much higher level of risk. If you release a new software-based medical diagnosis tool that is to be used in a clinical setting, you need to be very sure that your software is doing its job correctly, because if it's not, if there are bugs in your code, then you're going to be directly affecting people's lives. And for this reason, companies working in sectors like this are required by law to adhere to a range of software development standards and practices, which are put in place for a good reason to minimize the risk of bugs being introduced into the code. So this sounds very different to what I have personally observed and experienced as a software engineer in an academic research environment, and I'm sure that many of you will agree. But I don't mean to be too negative. I don't want to put too negative a spin on this. And based on what we've seen in the last two talks, I genuinely believe that research software development practices are improving over the past decade or so. The level of awareness of the importance of software has risen, and more focus is now being placed on the robustness of software tools that a particular research project has used. And I feel that even in some research circles, we're almost at the point where studies will only be taken seriously if they can demonstrate that the software they've based their work on has been developed in a robust manner, at the very least with automated testing and a formal versioning scheme. So I'm going to now spend a little bit of time talking about the types of programming languages that we use in research and why the choice of language often means that we need to be more careful and introduce additional safeguards when writing our code. So broadly speaking, programming languages can be divided into two different classes. On the left, I'm talking about compiled or strongly typed languages such as C or C++. And then on the right, I'm going to be talking more about interpreted or dynamically typed languages such as Python, MATLAB, and R. And I would hazard a guess that most research software, at least most custom software that's written by researchers for a particular study, is going to be written in a language classed as an interpreted language, such as MATLAB or Python. So when using a strongly typed language, we develop our code along by following this process. First, we write our code in our language of choice, then we pass that code to a compiler, which converts it into a binary executable. And once we've done that, we're able to run our program. In contrast, when using an interpreted language, the process is simpler. We write our code and then we just pass it directly to an interpreter, which runs it straight away. So using an interpreted language is simpler, but it comes at a cost. When using a compiled language, the compiler needs to read every single line of code. So if there's a basic error anywhere, such as a syntax error, a missing brace, a wrong variable name, or a call to a function that doesn't exist, the compiler will complain and you won't even get to the point where you're able to run your code. In an interpreted language, the interpreter will read the code as it gets executed. So if there's an error in the main part of your code, your program will crash, but there could be errors elsewhere in other parts of your code which don't get executed until several hours into the run, or which only get executed when an obscure command line flag is added. So these errors can be really difficult to find, as they may only manifest themselves when your software is run in a particular way. So when using a compiled language, we can rely on the compiler to eliminate a whole range of errors from our code, so that it's not even possible to make these errors or to introduce these errors into our code. But the compiler won't catch everything. It'll catch syntax and some semantic errors, such as invalid variables or non-existent function names, but it won't catch more obscure logic errors, such as an off by one error in a for loop. But things are worse when we use an interpreted language, because we don't have a compiler to rely on. So we run the risk of introducing a whole range of additional mistakes into our code. And so the point I'm trying to make here is that when we're using an interpreted language, we need to be a lot more careful. And ideally, we should be introducing additional safeguards which replace the job of the compiler to minimize the risk of introducing these errors into our code. And no matter how smart you are, you will make mistakes. There's just no getting around this fact. I work alongside people who are far more intelligent than myself, and yet I'm continually finding simple bugs that could have easily been avoided by adopting a few simple development practices. So I'm now going to go through what I think are 4 basic development practices or guiding principles, which I think everybody who writes software should follow in their own work. And if you follow these four guidelines, then it will give you a lot more confidence in the robustness of the code that you're writing. So I'm now going to spend a little bit of time going through each of these in more detail. And the first point is that you should be using a good editor. I've added the first point here regarding MATLAB because the MATLAB code editor is actually pretty decent. So if you're and ticks a lot of these boxes. So if you're using MATLAB, then you should just continue using the MATLAB editor. But for everybody else, if you're using a plain text editor to write code, then you're doing it wrong. It's that simple. At the very least, your code editor should be able to detect and highlight basic syntax errors, such as misspelled variable names or improper indentation if you're using Python. And ideally, your editor should be able to detect and highlight more complicated errors. If you're using Python, you can add type annotations to your code so that your editor will know the types of all your variables and will then be able to detect and inform you when they're being used incorrectly. And for larger code bases, features like automatic code completion, refactoring, and code navigation are just essential as they allow you to accomplish simple tasks much more quickly. So I'm just going to demonstrate some of these features very quickly using a Python-based development environment called PyCharm. So here's an example of a really basic Python error, which is where we've indented one line incorrectly, and the editor has detected this and informed us. Although, to be honest, this example is quite contrived because any Python editor, any half-decent Python editor wouldn't even allow you to make this mistake. If, in contrast, you're using something like Gedit, then it's really easy to make mistakes like this. So it kind of emphasizes that you really should be using a proper code editor. So the next example is one of code completion. So in here, the user has created an object called resp and has then typed .js. And in response to this, the editor has automatically popped up a list of suggested methods that could be called on this object. And so the user can then just choose an entry from this list and hit enter to complete the method name. And this example, again, is a little bit contrived because the completed method is JSON and it's so short that you could easily just type it out. But there are a lot of libraries which use really long function and method names, and code completion can be a massive time saver and will also reduce the number of mistakes or will reduce the chance of you making a mistake if you're alternatively typing out these long function and method names by hand. And so here's another example of code completion. This one is a little bit more sophisticated because it uses typing annotations. The episode ID input parameter here has been annotated as being of type int. And the editor has detected this and is then able to offer type-specific annotations or suggestions of all of the attributes and methods that are available on an int object. And finally, here's an example of refactoring. So imagine that we have this controller-based class and we just want to rename it to something else. If you are using a basic text editor, you would need to do a global search and replace across every file, or you would need to go by hand and search for every use of the word controller base and replace it. If you're using a decent editor, then you should be able to simply select or right-click on the controller base class name and select rename, and the editor will do all of that work for you. And so what we're essentially doing when we choose to use a good code editor to develop in an interpreted or even in a strongly typed, a compiled language, but I'll focus on interpreted languages such as Python, is we're replacing the job of the compiler. In a compiled language, the compiler is going to catch all of these silly typos and mistakes that we might be making whilst writing our code. A good code editor will highlight these mistakes and will offer code completion and refactoring features, which, if you use them, make it really difficult and sometimes even possible to even make those basic mistakes in the first place. And so I can't emphasize enough the importance of using an editor which is designed for the job. And if you're coding in Python, there are several options available to you. So I would personally recommend any of the first 3 options on this list, PyCharm in particular. The other editors on the list can be configured to work really nicely with Python. So in our first talk, we saw the use of Visual Studio Code, I think. But they require a little bit of work to set them up, whereas the first 3 will all work out of the box. I've got a couple of additional Python-specific points to make here. One of the most awkward and frustrating aspects of working with Python is managing environments. And I would wager that everybody who's listening to this talk has at least 2 or 3 Python installations on their computers, and probably even more separate Python environments. And it can become really easy to lose track of which Python environment you're using at any given time. So you need to make sure that when you're running your code, you're using the correct Python environment. And when you're using a particular editor to work on your Python code, that the editor is configured to use the correct Python environment. PyCharm can actually handle the creation and activation of Python environments for you. So I really would recommend it as one of the best options. And the second point that I'd like to make concerns Jupyter Lab and Jupyter Notebooks. I have to confess that I don't really use these all that much, but it seems to be getting better and better. Every month it's improving. And so I think that it is probably a good choice for developing code in Python. However, if you're writing your code as a Jupyter Notebook, you should be aware that your code may be slightly more difficult to share with others and to run on other systems than if you were writing regular Python code. This is slowly changing with the rise of online hosting platforms like Binder and Google Colab that we saw in the previous talk. But I feel that it's definitely something to keep in mind. And if you want your software to be as widely installable as possible, you might want to think twice before using Jupyter Notebooks. So on to my second guideline or principle. You should try your best to organize your code sensibly so that it is easy to test. And I'm going to demonstrate or start off by demonstrating this with a really simple example. This piece of code here runs linear regression. We give it a model loaded here as design.txt, and we give it some data loaded as input.txt, and it will scale the model to fit the data and return the scaling parameters or the parameter estimates and the residual error. And to be honest, this code, if this is all your program needs to do, then this code is kind of fine because it's so simple. I don't think it really warrants any restructuring, but I'd like you to imagine that this isn't a standalone script and is actually part of some larger, more complicated code base. And perhaps we're doing something a little bit more complicated than an ordinary least squares regression. And in that context, this code may not be ideal. First of all, this is a standalone script. So if we wanted to test it, we would need to call it from our shell environment. And again, for an example as simple as this is probably fine. But for larger code bases, this can become very tedious very quickly. So I'm going to propose an alternative design, which I argue makes this code easier to test and to validate. The code's obviously a little bit longer, but has some key advantages. So first of all, I've separated out the core algorithm that implements the OLS regression into a self-contained function. And second of all, I've put the procedural piece of code, which loads the input data and saves the result, into a separate function called main. And making these small changes has made the code much easier to test. The key difference is that all of the pieces of code on the right can be called programmatically. And apart from the main routine, which loads from and saves to files, there are no external or implicit dependencies or side effects in calling these functions. So every piece of software is different, and the particular task that a piece of software has to accomplish will dictate its design to a certain extent. And for this reason, I can't really offer any specific guidance or advice on how to organize any piece of software. But instead, I'm going to offer a few guidelines and pieces of advice that I would recommend you keep in mind when writing code. So the first piece of advice is to try and keep things simple and self-contained. Each function that you write should be responsible for doing one thing. And ideally, all of the pieces of information that the function needs should be passed in as input arguments. I mentioned earlier about implicit dependencies. So we can see, if I go back to the code, in the example on the left, this piece of code implicitly depends on the existence of the two input files, input.txt and design.txt. So this code can't even be executed, let alone tested, if those files don't exist. And so this is an example of what I mean by an implicit dependency. It's something which is not explicitly listed as being required by this code. And so you should try and avoid writing functions that have implicit dependencies, because when it comes to testing that function, you will need to take that into account. And similarly, you should try and avoid writing functions that have side effects, or at least keep those functions isolated from your core routines, which are doing the important work. An example of what I mean by a side effect is a function which, whenever you call it, might modify some global variable or global state, which could then change the behavior of the function the next time you call it, or of some other function in your code base. So this is kind of an analog of an implicit dependency. A function which has side effects will have an implicit effect on the behavior of other parts of your code. And this will have the effect that all of your code is just going to be much more difficult to test in isolation. So my recommendation is to try and write as much of your code as possible in this pure style, where there are no implicit dependencies or reliance on global states, reliance or manipulation of global state, where all of the pieces of information that are needed by a function are passed as input arguments, and all of the pieces of information that the function produces are explicitly returned. And so this brings me to my next piece of advice. Wherever possible, you should try and avoid or try and separate your core code, the code which does the number crunching, from any other code which loads and saves data, which reads settings from configuration files, and which interacts with the user. So the point of doing this is isolating your core routines from the messiness of the real world, from the user and from files and things, will make those core routines easier to programmatically call with some fake or test data. And if you're careful, you can also write your IO, your input output routine, so that they're also easily testable in isolation too. The ultimate aim here is to try and decouple all of the different tasks that your software performs into separate, isolated, self-contained pieces of code that are easy to call in isolation. If you can achieve this, then writing test cases for each of those pieces of code is trivial. So the next couple of slides are not really specific to testing, but are more focused on the overall design of your code base. So when you're developing some software, you should keep in mind the overarching structure of the code base. When you're enhancing or adding new functionality, and you should structure your code base so that it's organized in a clear, sensible, and logical manner. This comment specifically focuses on Python by mentioning classes, modules, and packages, etc. But the same concept applies regardless of which language you're using. Ideally, you should be using the constructs provided by the language to arrange your code sensibly. And the point of doing this is, for the most part, just to make your code easier to understand. If your code is split over dozens of files with obscure names in a single flat directory and with no evident relationship between those files, you're going to have a difficult time coming back to that code in 12 or 24 months from now to try and fix an obscure bug that one of your users has just reported. And you're also going to have an increased risk of accidentally breaking something when you go and change the code. And you'll also be making it more difficult in getting other contributors on board to work on the code base. In contrast, if your code is easy to understand and to reason about, then it will be easier to maintain going into the future. So I've already mentioned that I can't provide any specific or definitive answers as to how you should structure your code, as there's no one solution that will work for every piece of software. But what I am trying to do here is to get you to think about the bigger picture when you're writing and organizing your code base. And so on that point, while you're working on a piece of code, if you realize or start to feel that the current structure or the architecture of the code is going to cause scalability issues, both in terms of performance and in terms of scalability of the code base itself, the extensibility of the code, then you really should do something about it and restructure the code. If you have been writing tests whilst developing, in particular, something called integration tests, which I'll mention shortly, then you should be able to rearrange and refactor your code with absolute confidence that you will know if you've broken something. If your tests are passing and you make some changes and then the tests start failing, then you'll know which changes have caused the failure, and you'll be able to rework things until your tests start to pass again. And of course, it goes without saying that you should be using version control, and you should learn how to use it effectively. Because if you learn and apply the basics of Git, then you will have no fear whatsoever in tearing your code apart and rebuilding it. Because if you know how to use Git, it's trivial to experiment with and to prototype changes without worrying about losing or overwriting the version of your code that you know works. So it's a little bit, I feel it's a little bit of unfortunate, because I kind of feel that you can only really start to appreciate the power of version control, specifically of Git. I'm quite biased towards Git. Once you've learned how to use it. My guess is that people who don't really know how to use Git don't really understand why they need to or what all the fuss is about. But once you've learned, it opens up a whole new realm of possibilities in the way that you go about your work. And so I really do recommend getting to grips with it. So my next point is write code to test your code. So let's go back to our example OLS program and write some tests. So for most scientific software, in order to test some code, we're going to need some data. And for this example, I can easily just generate some toy data in the code itself. But it's just as easy to store some pre-generated benchmark data alongside your code, or to download it during the test while the tests are being run. There are an increasing number of programming libraries and frameworks which actually allow you to easily inject data into your code. For example, one example that I can think of is DataLad. And so you don't need to necessarily store your data set in your code repository. You can just download it when you run the test. But for this example, I've got my data just generated using a little bit of NumPy, and then this is my test case. It's really simple. It passes my test data to the OLS function, and then it checks that the result is correct. So in this case, I haven't added any noise to the data, and so I know that my parameter estimates are going to be exactly 5 and 20, and I know that the residuals should all be equal to 0. But it's quite easy to make the test criteria more sophisticated based on what I'm testing. For example, I could test that the standard deviation of the residuals is within some acceptable level of tolerance. And the way that I've structured my program on the right, my little example, has actually made it quite easy to test my main routine as well. All I have to do is save my test data out to some files and then pass those file names into the main function. Along with some output file names, and then I can just load those outputs back in and perform the same comparison. So I'm able to test pretty much every line of code in my little example. Obviously, however, real world code is going to be a little bit more complicated, and sometimes you have no choice but to introduce implicit dependencies or to deal with side effects in your code. But that doesn't mean that you can't test it. And in particular, Python has this amazing built-in library called mock, and there are similar libraries for other languages. What mock allows you to do is it allows you to mock or to fake specific parts of your code. You can mock your own code, but you can also mock functions from third-party libraries or even functions from the standard library in the same way. So in this example, the core routine that I want to test is this do analysis function. But do analysis has an implicit dependency. It loads some configuration parameters from a text file using the load parameters function. And I want you to pretend, for the purposes of this example, that it's not possible for us to just generate this analysis config txt file. For example, it could be in like a proprietary file format. But what we can do is we can mock out the load parameters function so that in our unit test, that function is always going to return a fixed set of values. So we can call, in our test case, we can call do analysis as normal, and do analysis will think that it's calling load parameters, but it's actually will be calling a mocked version of load parameters, which always returns 10, 10, 10. And so then we can call our function as normal and check that the result is correct. So if you're writing tests in Python, mock is just incredibly handy tool to have at your disposal. And there are similar libraries for other languages. So once we've written our tests, we need to be able to run them. And there are a few options for running Python tests, but I would recommend using PyTest and another tool called Coverage. in simple terms, PyTest is a tool which will, when you run it, it will just search through your entire code base, and it will find any function that you've defined, which begins with test, and it will run that function. And the companion tool coverage will, while PyTest is running, coverage is going to keep track of which lines of code were actually executed by your tests, and then give you a code coverage report. Basically, coverage will tell you which parts of your code were covered by your tests. So I'm going to tempt fate and try and show an example here. So, whoops, pwd. So I have a directory here which contains the same code that we've been looking at. So we've got analysis main.py. This contains my OLS routine. And then we've also got my tests, which are in test main.py, which is basically exactly the same that I was showing on the in the slides, just with a little bit more boilerplate. And so this is all of the code in my entire project. So I've just got my main routine, which is very basic. And then I've got my unit tests, which I have 2 unit tests, and then my data up here. And that's it. I don't have any other code. I have set up the environment so that I can run PyTest. So I've installed PyTest and I've installed NumPy and so on and so forth. But once all of that is set up, all I need to do is run PyTest, and it will scan through my code and find all of my test cases and run them all. And so what I'm going to do now is just to show you how easy it is to add additional tests. I'm going to add an additional unit test, which, because this example is so simple, I don't normally run Emacs like this, so that's why it's giving me all of these warnings. I have Emacs running separately, actually in a separate window, so ignore all of those warnings. But what I'm basically going to do is just add an additional unit test and then see what PyTest does with it. So just to distinguish my second test from the first one, I'm just going to scale the data so that it's so that then I can expect that the scaling parameters will be well, twice as big as they were in the original test. So that's done. And now if I quit out and then run PyTest again. So in the previous invocation, you can see that it ran 2 tests, test OLS and test main, whereas in this next invocation, it's automatically picked up my next unit test. So all I had to do was write the test and it just gets run straight away for me. So it's super easy. So back to the slides. Right. So I've got a few guidelines on how to go about writing these tests. So first of all, it's much easier to write tests for a piece of code whilst you're writing the code itself. Once you've decided that you need to write a function which performs a specific task, you should already be able to start thinking about how you might go about testing that function. It's usually much more difficult to write tests for existing code. If you write a bunch of code and think, oh, I'll just get it finished now and we'll add some tests later on, there's a good chance that you will not have written the code in an easily testable way. And there's a very good chance that you're just never going to get around to writing those tests. So I would recommend writing your code and writing your tests in parallel and regularly running the tests as you develop the code. It's sometimes even possible to start with the test case, and developing in this way will really help you to understand and to trust your code a lot better. In particular, its edge cases in a lot more detail. It's also really helpful to write tests which probe your code at different levels of detail. So up to this point, I've been talking primarily about unit tests, and this is where we have a single piece of code, such as a function, and we just want to test that one function. There is another class of tests, though, which I'm referring to as integration tests. And these are just as, if not more, valuable than unit tests, as what integration tests do is they will test your program as a whole to make sure that all of the individual components are working together. And so I'm just going to try and quickly show a couple of real-world examples of what I mean by unit integration tests. So this is the Fossilize, which is one of my main projects that I work on. Fossilize is an image viewer, and it has this feature that allows you to annotate the image view, the orthographic canvases. So you can write text and you can draw arrows and things to highlight particular parts of anatomy. The idea is to if you want to create a screenshot for a figure, you can just draw within Fossilize. And I have a unit test for every single annotation type. And you don't need to understand how the code works, but the point that I'm trying to make is that I have a separate test which tests one specific little piece of functionality. So I've got a unit test which tests the line annotation, which is just where you draw a line. I've also got an arrow annotation, and I've got a unit test which tests that. And I've got a test for rectangles and ellipses and text, etc., etc. So this is an example of some unit tests, and I want to contrast that with some integration tests that are part of my test suite. So here I've got a module which tests the 3D view in Fossilize. So this is where we take an MRI volume and we render it in 3 dimensions. And so my integration tests for the 3D view are actually, they're all command line invocations. So Fossilize has an extensive command line interface where every display setting that you can control within the application can also be set on the command line. And so this basically comprises my set of integration tests for the 3D view. They test the kind of the end-to-end 3D functionality. Each of these command line invocations will be within, when the tests get run, will be executed, and the result will be saved to a PNG file. And it will then be compared to a benchmark, an existing pre-generated PNG file that contains what the scene should look like. And so this is, I just wanted to show some real-world examples of how you might code up some unit tests and integration tests. So now if we go back to the slides. And so I also personally think that there's a lot of value in what I refer to as sanity check integration tests. For example, if you're writing a command line program, you could add my program -help as a test. And the sole purpose of this test is just to ensure that your program doesn't crash when the user asks for help, because it's really easy when you're making changes, when you're fixing a bug, to accidentally make a mistake somewhere and introduce a critical bug that causes some other part or some other aspect of your program, which you probably never run yourself, to crash, such as asking for the command line help. And so I have a range of integration tests which test really basic functionality like this, like, can my program be opened up and be closed down cleanly? That's another example of an integration test. And so whenever I make changes to my code, all of those tests are executed. And so I know very quickly whether I've broken something. So another very important class of tests are called regression tests. And these kind of tests are added in response to bugs. Whenever, and we saw this in the previous talk, an example of this. Whenever I find a bug, the first thing that I'll do is write a test function which can reproduce the bug. And then while I'm working on the fix, I will periodically be running that test case to check whether I've fixed the bug or not. And when the test case passes, I can close the bug report and I know that the bug's been fixed. But once you've fixed that bug, you should keep that test case around, because it's really valuable. It encodes a particular piece of behavior or piece of logic which your code must adhere to. And if you add it to your test suite, your collection of tests, and run it regularly, then you will know if that logic or behavior is ever broken in the future, and you will know that it needs to be fixed again. And it might not sound obvious as to why, once you've fixed a particular bug, why would it ever crop up again? But believe me, it does happen quite regularly. So we're on to the final point. I've given you an idea of how you can run your test suite by hand on your own computer. If you're using Python, for example, use PyTest and coverage. But a much better option, and again, as we've seen, I'm just going to emphasize what's been shown in the previous talks, is to have your tests run automatically whenever your code changes. And if you're using GitHub or GitLab, this is really easy to set up using something called continuous integration or continuous delivery, or CI. And the way that this works is as follows. So you make some changes to your code and you commit them and push them to, for example, GitHub. GitHub will get in touch with the CI provider and will notify it that your code has changed. the CI provider is going to start up a Docker container or a virtual machine running somewhere in the cloud, and it's going to, it's possibly even a physical machine if you, for example, need to run tests on Mac OS, or if you need to use a GPU to run your tests. And then your code is cloned to the container or VM, and the CI provider is going to run a script which you have prepared, which sets up your environment, installs dependencies, builds your project if necessary, and then runs your tests. And so I mentioned the term, or I'm using the term CI provider, but these days you can actually do everything from within GitHub if you're using GitHub. So GitHub can host your code, and it can also be used for continuous integration using something called GitHub Actions. There are, however, a number of other CI providers that can be integrated into GitHub, which for a range of reasons you may prefer. For example, AppVeyor has much more comprehensive support for Windows. I can't really remember the other ones. Some of them I think will offer, if you pay, you can actually run your tests on hardware, for example, particular GPUs, that sort of thing. If you're using GitLab, and this is what I generally personally do because we have our own GitLab instance, you can set this system up so that you can actually run your tests on your own hardware, and this is really useful. And as an example, I mentioned that I do this for most of my own projects. So this is my bookshelf at home, and you can see that I have an old MacBook laptop sitting on my bookshelf, which is always on and always plugged in. And I use this to run Mac OS specific tests. And so I'm sitting up in my office right now, but what I can do is when I'm working on a piece of code, I can write some changes, I can commit them, push them to our GitLab, and then after a few minutes, I can hear the fans start whirring on my old MacBook as these CI jobs get scheduled and start running. So it's fairly straightforward to set this up on your own hardware. So, and by the way, the reason that I'm using my old MacBook is because we just don't have a lot of funding for this sort of thing. And I mean, waste not, want not, right? So I've set up an example project on GitHub, which contains the OLS code and associated tests that I've been presenting. And you're welcome to go and have a look at this in your own time. And I've set it up using GitHub Actions so that whenever I push changes, I have these unit tests run automatically. And I mean, this was demonstrated in the previous two talks, so I'm not sure if there's any point in going over it again. But I'll bring up the repository quickly here. Why don't I just add that extra unit test? Add test main. So I have some aliases, so I'm too lazy to type git, so I just have an alias to G. New test. Whoops. Main. Okay, so I've just added my new test, and you'll see if I refresh this page, new test, there's a yellow circle here, which is, okay, yep, my pipeline has been started. And again, as you saw in the previous talks, all of this is driven by this little piece of YAML code, which I prepared in advance. And the bulk of it is actually down here. So I've checked out my code, I've installed Python, and then all I'm doing is creating a virtual environment. I'm installing my own little project, which handles dependency installation, and then I'm running PyTest, and that's really it. And GitHub has this actions thing. New test, I have a tick, so that tells me that it all worked fine, no problem. And you can see here, it's installed dependencies, it's run my tests, it's run all 3 of my tests, including my new one, and that's that. Yeah, I think that is pretty much the end of my talk. So just to recap, I've introduced 4 basic guiding principles, which I strongly encourage you to adopt in your own development workflow, because they will really genuinely help you to minimize the number of errors that creep into your code. So first of all, use a good editor, which to reduce the number of mistakes that are possible to make. Organize your code sensibly to make it easy to test and easy to understand. Write code to test your code. write unit and integration tests while you're developing the code, and then write regression tests in response to bugs. And finally, you should be running those tests regularly and ideally automatically using continuous integration. So yeah, that's it. Thanks very much for listening, and thanks again so much to the organizers. And yeah, happy to take any questions.
Thank you, Paul. Thank you. It was really great hearing about the best practices in testing and why it is important. I have one specific question regarding testing that I've always had, and mainly when I see tests and automatic tests being deployed, it's deployed in small projects or projects that can be run in a sensible time. But these days, deep learning projects are getting more and more. So are there any specific test procedures for deep learning based projects that take maybe the days or weeks to train, or is it just the same?
So there's, I think it comes, this can be addressed somewhat by good code design. Like ideally, like if you're really thinking about the design of your code while you're developing it, ideally, or at least I strive to write functions which will scale. So functions which can be executed with a massive data set, but can also can be executed with a really small data set, and which will then run very quickly. And so this is what you should ideally strive to do. And if you can achieve that, then it makes testing easy, because you don't need to test at scale. You can just test with your little toy data sets. Obviously, in some circumstances, that's not possible. And so another approach is to have different categories of tests. For example, you might have a small, fast suite of tests that'll only take a couple of minutes to run, and that you can run on every commit. But then alongside that, you might have a more comprehensive test suite that you will use when you're preparing for a new release, for example, or just when that might take, for example, my full fossilize test suite. It doesn't take that long, but I run it for different platforms and for different versions. So all in all, it takes about 5 or 6 hours to run. So I don't run that all the time. I only run it when I'm ready to merge a new feature in. At all other times, I'll just run a fast set of tests. So they're probably the two main approaches, I think.
Perfect. Yeah, I think that completely makes sense. Thank you, Paul, and thank you all our previous speakers, Sebastian and Martin, for the great talks. I think we are out of time, so I'll just end this session. And once again, thank you for your contribution and your great talks. And just to mention that there are 2 remaining sessions in practicals that are following in the next hours. So please join them if you are interested, and hope to see you all in another session. Thank you.
Thank you.